どういうなんかあるよね。なんかあるじゃん。
180番、181番でお待ちのお客様。お待たせしました。
Q&A session. But feel free if you have questions during the way, you can type them as a private question, and I will read them off and discuss them at the end and address them as best I can. And then the second logistic thing is that there will be an exit survey, which will be about 5 questions that you can, if you would please answer. It should take you about 30 seconds, and it'll help us to let us know what we can do to make this webinar series more productive and useful for you in the future. So if you keep those 2 things in mind, questions and answers at the end of the presentation, type them as you go along, and also there will be an exit survey that you can cover. It'll take a few seconds, 30 seconds, it's 5 questions, and we'd appreciate it if you'd answer. Thank you very much. So without further ado, we can begin discussion on the stylus and optical metrology tools that we have, which will help in solar metrology, solar cell manufacture, and process monitoring. This outline here is just a brief. It shows 5 sections. Really, there are 4 sections, and then a summary. I'll briefly cover, just why process control, where does the demand come from. I'll talk for a brief moment about the market for solar and photovoltaics, and just give an overview of those things, and then an overview of the fab processes. And after I finish going through the background material, I'm going to talk specifically about the things we do here in the Stylus Optical Metrology unit for Nanoservices division, things that we can supply to you as manufacturers or people in the development of solar materials, photovoltaic materials, the types of things we can offer for metrology and process monitoring. So first, I just, as a curiosity, just kind of talk a little bit about process control. Bruker and the Stylus Optical Metrology business unit have a history of providing QA and QC type solutions for different industries, and most notably the hard disk industry, but also in semiconductor. And now, as things move forward in solar, there are different technologies that people are developing, and there's basically a drive to have good quality products, and anytime you can control process along the way, you can save costs and improve yields. So, what I did is I just looked for recent discussions in various areas on the internet, just to take some examples of people speaking about this. Here's a fellow, Mike Lisinski, at Rudolph Technologies Data Analysis and Review. He's talking about the increased competition for both crystalline and film photovoltaics. There's increased competition, and there's a need to use intelligent data to make the lines more productive. And so instead of just trying to differentiate on efficiency, now they're trying to make better product quality and improve product quality along the way as well to gain market share. Here's a different flavor of driver for process control. This is a researcher. He's a fellow from Ohio State, and he's the Chemical, Biological, and Environmental Engineering, and he's working in large thin film absorbers on a glass substrate, and he mentions right away that process control is needed, testing the finished solar cells in order to improve efficiency. So these are 2 vastly different places where this is done, and then yet a third example. Last September, at the European Photovoltaic Solar Energy Conference, a company called Qcells introduced laser marking, and they did a demonstration where they could show that during process they could make laser marking, identify modifiers, which can then, correlate to each process step and allow for metrology to take place in line to know the steps and identify materials along the way. So this is something that's been, and the need for this has been around for many years. I read a paper from 1999 that the NREL folks, and it mentioned already starting to look for needs for process control. So now I'm going to give just a brief overview of the current market, and this is possibly not new, but it's just interesting information I would like to share, and it sort of sets the groundwork for what is trying to be done currently. We have various competing technologies in solar. The mono and polycrystalline silicon. We have, the straight material appears. So there's different thicknesses. Sometimes they're being sought thinner than this, I think, but the efficiency is 25%, and it's used in residential consumer products. This is the majority of the market. You'll see. I'll show you some of the information later. We have the 3,5 compounds and multi-junction type devices that have different thicknesses. They're metal organics, CVD for deposition and used in space, some terrestrial work. Different efficiencies there. I'll show you some numbers where I get these numbers from current efficiency. The thin film materials, which can be, they're lower efficiency and they're also lower market share now. So there's a wide range of technologies, but all of these can benefit from good metrology at various steps in the processing to help control and monitoring the techniques used. So the next slide is just an overview. It shows a chart showing the different technologies as how much of the market is currently taken by those, and currently it's roughly 85% in 2010 for the mono and multicrystalline silicon. Then there's the amorphous silicon and ribbon thin film type things, the copper indium selenide type stuff, and take up smaller pieces at the top. But that's not to say that those things are not being worked on and still in need of metrology for improving and controlling the process used to make those devices. And I just thought I'd share, this was last updated in April 2011. This is a chart from National Renewable Energy Lab, and they basically are showing what is the current best case research efficiency, so kind of pushing towards theoretical limits for things. And this is where I've, these aren't production numbers that I put, but they're, these are the limits that people are working towards surpassing, and eventually you come to theoretical limits for efficiency. But these are the different technologies. In the purple, you have the multi-junction devices, which get up to the highest levels of efficiency. The crystal, mono, polycrystalline silicon, and then merging devices down at the bottom that have somewhat lower efficiency, but they're different newer technologies. So energy cost and demand are the real market drivers for solar and for moving performance to be improved at lower costs. Here's a picture of the Moscone Center in San Francisco. It's covered with solar cells, and it's one of the largest municipal banks in the United States, I believe, if not the largest, I think, in terms of municipally owned in San Francisco here. And these different things that increase energy demand, the cost of energy, as well as diminishing fossil fuel reserves, environmental concerns and regulations, combined with the world demand for energy that is predicted to more than double by 2050, means that there are considerable market forces that mean it's a worthwhile choice to try to go push for solar. Additionally, currently, solar lags fossil fuels in terms of cost per kilowatt hour by roughly a factor of 10. And so the economics of solar are such that it is not yet competitive, but the global regulatory environment has increased the incentive for pushers. One of the ways as efficiencies are increased towards their theoretical limits to improve on costs, and the economics of solar will be to improve the process that people use to make the cells and the technology. So now that we've gone through a brief overview of the market, what are the kind of drivers for solar as an energy production technology, we're going to look just briefly at the fab processes used to make these different devices. And I want to categorize this as more just a very broad overview. I'm definitely not an expert on the fabrication processes here, but rather I'm showing these examples as just illustrative of the different steps that are taken and the different things that are done along the way during the manufacture of the different devices, and trying to show that you can imagine along the way there are many ways that we can apply metrology in an intelligent way to control or to monitor what is happening at these steps. So the first slide is basically just a silicon-based manufacture with chemical etch and texturing. The texturing is there to bring down the reflectance of the surface, and then doping and edge isolation. So you do a laser etch around the edge of the cell in order to make sure that you don't have short-circuiting. Then AR coating with silicon nitride, and then metallization for production. All along this way, there are several processing steps. You can imagine that potentially you want to monitor what the surface texture is, what is the quality of the isolation, the quality of the AR coating, etc. There are many steps where things can be stopped if something is going wrong in order to save material cost or to save further capital investment in terms of quality substrates, for example. The 3-5 materials, here's another simple diagram that shows the steps in the process here, and looking at the metal organic deposition, then etching, metallization for conduction, and then AR coating as well. These are the higher efficiency type devices, and there are definitely gains to be made if you can ensure quality along the way during the processing here as well. Here is a similar slide for the large silicon substrate type devices where you have several different steps with laser scribes in between, which are used to separate the layers in terms of conductivity and to ensure isolation. And then you have the deposition of the semi-layer and then metallization. And along the way, there are various things that you can do to check the quality of what's happening in the process. Show and get into some of that in the section. Again, same type of picture for 6-type devices, 10-type devices. Here's again the scribing and annealing processes. Along the way, there are different steps that we can check the quality of the steps and ensure that we have good quality material coming out at the end of the process. So what I'd like to focus most of the time on here is what is it that we do here at Bruker in the Stylus Optical Metrology Unit where we can help to enable good quality control and good understanding of the processing steps that you have that we've just gone through. So the surface metrology can help to monitor process steps. All the various steps that we just discussed can be inspected via stylus and optical metrology methods, 3D methods, optical microscopy. The stylus systems that we made here in Tucson can be used to measure surfaces, step-height stress in a film can be used to measure and monitor trace widths or trace uniformity. And we also have complementary 3D optical microscopy, which can make measurements of the trace widths in a faster manner, paste uniformity, isolation, etching, 3D surface texture. And one of the very unique things about the optical metrology is that you can, as well as doing these other types of measurements, you can use specific 3D surface texture to correlate directly to product efficiency, which is a very important step if you want to be able to quantify how well the end product will function. If you can quantify that by making a very specific measurement of surface texture and correlate it to end product efficiency, you have a key look at what the bottom line will be. So the stylus systems that we have, this is the most recent product launch we have, is the NextAct XT. It is an incredibly versatile tool that can be used to measure the conductive stream thin film deposition, monitoring. You can look at laser scribing, how the depths or edge in laser scribing. Thin film stress can be measured. You can see that this is something that can be used traditionally been used in a 2D way, but we can also make multiple scans to provide a 3D trace. A 3D map of a solar trace, for example, here is one of the examples of a cost-effective and, if not fast, way of making the measurements. This is certainly faster than competitive tools. We've made some great improvements and enhancements to the deck. Yet among the fastest stylus instruments, if not the fastest, combining very high 5 angstrom, sub 5 angstrom type resolution. So this is an excellent metrology that we provide here to make these types of quality improvements. Another of our capabilities, and this is sort of a complementary and additional capability, are the 3D optical microscopy tools that we offer. The Contour series, the K and the X series profilers, as well as the NP Flex profilers. I've shown a picture here of one of the Contour. This is actually the Contour GTX that's here. But there are various grades of the profilers that will support tabletop research applications or product process development type applications, if you will, up to a fully automated system which can handle wafer handling and do parts handling type in conjunction with the wafer handler to make a production line metrology capability. And what I'd like to highlight here is that we've integrated basically we've taken and built off of our research and experimentation in this area of correlating efficiency in solar cell manufacture to build some custom analyses that are available in Vision 64, which is the operating software for our optical profilers, which are specific to the solar process industry. We can look at heights and slope histogram analysis for pyramid structures on solar silicon crystalline structure. We can do fast 3-dimensional traces of solar paste. For example, here you see a broken trace, which will lead to lower efficiency and wasted real estate on the cell. We have the auto computation of the 3D surface parameters, which I'll talk a bit more about, but these directly can be correlated to end product efficiency. And just an aside, on this slide, I'd like to mention, we at Bruker here in the SOM group, we offer both confocal and white light 3D microscopes. Non-position confocal microscopes as a tool for monitoring the process and correlating to efficiency for solar cell. And I want to stress the reason for that is the Confocus tool does not have the large field of view capability with the adequate vertical resolution.